Section 6.2. The differential forms of U, H, A, G. First, let's look at du. du is equal to dq plus dw. For a reversible process, it's dq reversible, and dq reversible is TdS. dw reversible is negative PdV. Now we have the exact differential form for du, that's TdS minus PdV. How about dH? H is defined to be U plus PV. Therefore, dH is equal to du, this is du, plus PdV plus VdP. This part is the exact differential of the product of PV. The result is TdS plus VdP. This negative PdV and this positive PdV cancel. How about dA? A is U minus TS. Therefore, dA is again du here. This is du from here. Minus TdS minus SDT. The result is negative SDT minus PdV. Finally, dG. G is H minus TS. So this part is dH. It comes from here. And then minus TdS minus SDT. This is the result. So these differential forms are useful because if we have a fixed amount of a substance, we know when dt is 0, dp is 0, then dg is 0. Also, we can use these four equations to derive the Maxwell relations. Now let's look at this. If du equals TdS minus PdV, we know delta U over delta S under constant volume condition is T. How do we understand this? Let's look at the subscript. This V means constant volume. When the volume is held constant, this dV is 0. Therefore, du equals TdS. du over ds is T under the constant volume condition. Over here, du over ds under constant volume condition is T. Similarly, if we hold entropy constant, this part is 0. Then du over dV is negative P. du over dV is negative P under constant entropy condition. Well, since we're holding one variable constant, we put it in the subscript and we change du with delta U, dV with delta V. So we have this first derivatives. And now, remember in calculus, we have learned this. Since U is a state function, the second derivative of U with respect to S and V, or in a different order with respect to V and S, they should be exactly the same. So yes, indeed, U is a state function, and delta U over delta S on a constant volume condition, that's T, temperature. So basically this part is delta T over delta V, delta T over delta V. Now we have this delta U over delta V on the constant entropy condition. That's negative P. So we can replace this with negative P from here. And then we get the first Maxwell relation. Delta T over delta V on the constant entropy condition is equal to negative delta P over delta S on a constant volume condition. Similarly, we can start from dH. dH is equal to TdS plus VdP. And then if P is constant, this part is 0, and dH over ds is T. dH over ds is T. If the entropy is held constant, dH over dP is V, so over here. And then again, H is a state function, therefore the second derivative of H with respect to S and P, or P and S in a different order, should be exactly the same. And then we get delta T over delta P is equal to delta V over delta S. Pay attention to the subscripts. Again, we replace this part, the top part, with this T. We replace this part with this V. Now let's look at dA and dG. dA is equal to negative SDT minus PdV. When volume is constant, dA over dt is negative S. When this temperature is constant, dA over dV is negative P. Therefore, we have these two equations to use. And A is also a state function. Therefore, we can take the second derivative of A first with respect to T and then V, or first with respect to V and then T. It doesn't matter. Delta A over delta T is negative S. delta A over delta V is negative P. And then we get this very useful equation here. Why is this useful? It's very difficult to measure the entropy change. It's a lot easier to measure the change of volume, pressure, and temperature. So really, if we want to measure how entropy changes with volume, we can simply measure how pressure changes with temperature under constant volume condition. And we get the formula here. And then we can integrate this ds with respect to this part dv. Now let's look at dg. dg is negative s dt plus vdp. Therefore, when pressure is constant, over here, dg over dt is negative s. Over here, dg over dp is simply v. And then we have the second derivative of g with respect to t and p, or p and t. We get this information. Actually, this one is also very useful because, again, now we know how entropy changes with pressure. Why? Because we can simply hold the pressure constant and see how the volume of the substance changes with the temperature. We get that relation here, put it in here. And then we move this dp to the right-hand side. And then we integrate both sides to get the change of entropy under a constant temperature condition. And also, there's another use of these two equations. Why is this? We learned how to derive the internal pressure. No, we didn't learn that. We know the formula of the internal pressure, delta U over delta V. Now we can derive this. Delta U over delta V at constant temperature is simply, well, this part, du is TdS minus PdV. So delta U is T delta S minus P delta V. And we put delta V here, and then we do a division. So this part, P delta V over delta V is simply P. And then we have T times delta S over delta V. And under this isothermal condition, therefore we can take this T out of the derivative. It's going to be T times delta S over delta V minus P. All right, so this minus P comes from negative P delta V over delta V. Now, what about this part? Delta S over delta V. Well, if we screw up a little bit, delta S over delta V is delta P over delta T. All right? But pay attention to the subscripts as well. This subscript is T. That subscript is V. So just be sure you get the subscripts written correctly. And now we have the formula of this internal pressure. This is how internal energy depends on volume under constant temperature condition. It's T delta P over delta T with this V in the subscript minus P. Similarly, we can derive the variation of enthalpy with pressure. So it's here, delta H over delta P under constant temperature condition. dH is TdS plus VdP. And then TdS over dP is just, T times ds over dP on a constant temperature condition. The second part, V delta P over delta P, that's just V. So I copy this V here. And now let's look at this part. Delta S over delta P, it's here, delta S over delta P. Negative delta S over delta P is delta V over delta T. So we have delta V over delta T with a negative sign here. So this is how we derive the formula of the internal pressure over here. This is the variation of the internal energy with volume, and also the variation of enthalpy with pressure, using these two Maxwell relations. Well, of course, there are other two Maxwell relations. They are also useful.